Hello and welcome to Lesson 15, the final lesson in this course on Introductory Polymer Rheology. This lesson is going to give 3 case studies on how to characterise complex fluids, which I hope will be of practical use to you. The first part of this lesson is going to examine how to obtain the linear and non-linear viscoelastic response of a commercial grade of polystyrene, PS680E, using a combination of rotational and capillary rheometry. All experiments will be done in the melt phase between 170 degrees Celsius and 200 degrees Celsius. What we'll see is that knowledge of the linear and non-linear viscoelastic response can also help us to check apparent viscosity measurements, enabling us to obtain a high quality set of data. So let's start by examining why we might want to do this kind of characterization in the first place and see what uses we can put the resulting data to. Now, if we outline some aims to start with, we'll then talk through the uses and then we'll talk through some methods. So in terms of aims, let's say first of all what we want to do is to quantify the linear and non-linear viscoelastic response of a commercial polystyrene. Okay. Let's also say what we'd like to do is quantify the shear viscosity as a function of shear rate for the same material, so we end up with apparent viscosity data. Let's say a third aim would also be to have confidence in the data that we've measured, and we'll see how using both the linear and non-linear viscoelastic response in combination with the shear viscosity response can allow us to do that. So, why might we want to do this? This goes beyond the academic. There's got to be a practical reason why we're spending resources, time, money, use of equipment to actually do these characterizations in the first place. So let's think of some good solid reasons why we may want to do this. So the first reason is quality control. Imagine for a minute that you're running a polymer processing line. It might be film casting, it might be film blowing, it might be some kind of injection molding. What you want to do is to ensure that that line runs stably all the time. In the case of, for example, film casting, the stability of that cast film strongly depends on the viscoelastic nature of the polymer that's being extruded. These lines will vary very differently in their behaviour depending whether you're extruding, say, a linear polyethylene or a high molecular weight polystyrene or some kind of polypropylene. So the architecture molecularly of the polymer, which we know affects the macroscopic rheology, is going to strongly determine whether, in the most extreme case, these materials extrude or not, but more pertinently, how stable they're going to be and whether you're going to get the kind of product that you want. So looking at the viscoelastic fingerprint of the material that you're using in these lines enables you to make a very good judgment as to whether or not that material is A, going to work, and B, is consistent with materials you've processed on that line before. You might, for example, have 3 different batches of polystyrene in the warehouse. You might be processing one batch and it all works very, very well. You might process a second batch and it has the same apparent viscosity data, but maybe it doesn't work quite so well. And the reasons why it won't work quite so well can be discovered when the viscoelastic fingerprint's looked at. So the first use we can put these data to is really quality control between different batches of polymer on a manufacturing line. And looking at the viscoelastic response enables you to see very clearly whether or not these polymers are actually going to behave as you think they are. So a second use we may put these data to is for engineering calculation. Now, full viscoelastic calculations for engineering flows are challenging. They're certainly possible using computational methods. There's a lot of modern computational tools that one can get hold of now to allow you to do this, but they're very time consuming, they're very computationally expensive, and they may yield more information than what you actually need to try and complete the task that you're doing. So there's still a lot of value in having a good generalized Newtonian apparent viscosity model to do some quick estimating calculations with. And so what we can obtain from these data is exactly that, a good generalized Newtonian model of the material response at a given temperature. So we might also want to do some quantification of relaxation time. Now, again, let's put this in the context of a solid example. Let's say you're, again, let's stick with the cast film line, you're film casting. You're making a cast polymer film and a short while after the material is extruded from the die, you're cooling it using maybe chilled rollers or something of that nature, or maybe an air quench. So, how much stress is locked into that polymer once it's set, once you've chilled it, once you've solidified it? That's going to be a function of the longest relaxation time of the material. It may not be an issue. For many uses, if there's a little bit of embedded stress within the final product, it may not matter. However, there's times it does. For those of you who have soaked your mobile phone, taken the SIM card out and dried it with a hairdryer, only to watch it crinkle up into something shaped like a Pringle, as a result of stored stress being relaxed, you will realise that sometimes stored stress can be a problem. So, if we want to gain a measure of how long stresses take to relax, again, these kind of data are going to be very, very useful. So how are we going to do this? Well, we're going to use two methods of rheometry. The first is parallel plate rotational and oscillatory rheometry. We're going to use 25mm diameter parallel plates, and the data that I'm going to show you is from a controlled strain rheometer, an Aries rheometer. You might well ask, why aren't you using a cone and plate? Because cone and plates give you, if you like, purer measurements, and that's entirely correct. From a practical standpoint, for polymer melts, the first thing that is going to destroy the quality of your data is poor contact between the polymer and the surfaces of the rheometer. So the way that you prepare a sample for melt analysis would be to get, say, a sheet of polystyrene and to stamp out a 25mm disc, solid disc. You could then put that between your rheometer plates, put your plates together, wrap the plates in the provided oven, get the rheometer to temperature, push the plates together a little bit more just to ensure you've got good contact, and you can see how much contact you've got through the normal force measurements, and then carry out your experiments. With parallel plates, it's a lot easier to get good plate polymer contact than with a cone and plate. How can you guarantee with your cone and plate that you've actually got good contact all across the angle of your cone? With a solution or something you can load in a liquid phase, that's relatively straightforward. With something that has incredibly high apparent shear viscosity at melt temperature, for example 10,000 or 15,000 Pascal seconds, this is a harder problem. And so very often one would use parallel plates because you can guarantee that it's easier to get good contact between the material and the measuring plates. What we'll see later in this part of this lesson is that one rheometer can only get you so far in terms of data. And so I'm going to use a second type of rheometry here, capillary rheometry, using a multipass rheometer. It's a fully contained device, as we've explored in lessons long ago now, and that enables us to do multiple experiments on the same batch of material. I'll be using 2mm bore capillaries of varying lengths, so those varying lengths allow us to do a Bagley correction and to ensure, again, that we've got good quality data. So those are our aims, those are our uses, those are our methods. Let's get down to the heart of this and see what sort of data we can obtain and see what kind of protocol we could perhaps follow to make sure that we have a good analysis. So the first thing I'm going to do is to identify where the linear viscoelastic region lies. I'm going to do this using oscillatory rheometry in parallel plates at a fixed angular frequency but at varying strains, and we'd call this sort of experiment a strain sweep. So I'll put some data on the blackboard for you and we'll then talk through it. What I'm plotting on this graph are the two moduli, the elastic and viscous moduli, and the apparent and the complex viscosity. The complex viscosity is the green crosses, the elastic modulus is the light blue circles, and the viscous modulus is the sort of salmony pinky kind of circles. The angular frequency I've chosen is 10 radians a second, relatively arbitrary choice, and I'm sweeping strains between about 0.01% up to a few 100%. So I've got several orders of magnitude here of strain that I can examine. And if we look at the data on the board, what we can see is there is a very large region where there is no strain dependency on the data. This is what we call our linear viscoelastic region. And we can see up to about 50% strain, the polymer behaves linear viscoelastically. A lot of the data that we're going to obtain in the next parts of this lesson requires linear viscoelastic analysis, and so it's important that we know where the linear region is so we can do those experiments correctly. So what we're going to do is we're going to obtain linear viscoelastic parameters using about a 10% strain with our rheometer. 10% just because it's less, significantly less than 50%, and it keeps us on the safe side. Why not lower? Experiments will take longer. So it's a compromise between making sure that you can get the experiments done in a timely manner and also keep the strains well within the linear region. So the next experiment that we might do is a frequency sweep. What we want to do is to look at the frequency dependence of our elastic and viscous modulus. Again, I'm going to be using parallel plates, and we're going to now keep a fixed strain. We're going to do our experiments at that 10% strain, so we know we are in the linear response region of the polymer. And again, I'm going to put a plot on the board and then talk through it. This plot again has the same symbols as the previous plot. I've got my two moduli, my elastic and my viscous modulus, in light blue and salmon pink respectively, and I also have my complex viscosity in green crosses. The strain I'm using is 10%, and I'm sweeping angular frequency from about 0.01 radians a second up to 100 or so radians a second. If I was to go below 0.1 radians per second in terms of angular frequency, which you're perfectly capable of doing, you should prepare for a long wait, because taking multiple measurements at a few hundredths of an angular, few hundredths of a radian per second does take rather a long time. So again, assess what data you need over what frequency ranges you need, and that enables you to determine whether or not it's worth spending the time getting those data. In terms of the results on this plot, what we can see first of all is a region where viscosity dominates the response of the polymer. G double prime is greater than G prime. At low angular frequency, we can see that the viscous modulus, G double prime, is an order of magnitude greater than the elastic modulus. However, as we increase in frequency, the disparity between those two values narrows, and there's a region where the viscosity and the elasticity contribute equally to the polymer response. So what we see then is a crossover frequency and then an elastic dominated part of the polymer response. So the crossover frequency is roughly 40 radians a second. That is where the viscous modulus and the elastic modulus are equal. And above that crossover frequency, for this polymer, over this range of angular frequencies, we can see that we then get to an elasticity dominated region. Okay, so all very interesting. Now, what we want to do is to start to quantify these data and start to process them. So what we're going to do next is to use those frequency sweep data to obtain a relaxation spectrum, and then to do some calculations using that relaxation spectrum to make sure that it is indeed appropriate and we can backfit the experimental data that we've just obtained. So if you recall from previous lessons, we can calculate G prime and G double prime as a function of angular frequency using the relaxation spectrum parameters Gi and lambda I, the relaxation modulus and the relaxation time. So if we've got good values of Gi and lambda I, we should be able to calculate good values of G prime and G double prime. Now, we talked a little bit about relaxation spectra in previous lessons. This relaxation spectrum was obtained using the Aries inbuilt software. We can see that it's chosen a logarithmically spaced range of relaxation times from 0.01 seconds to 10 seconds, and it's correspondingly calculated values of the modulus Gi at each of those relaxation times. So what does that give us? Let's see what the calculated G prime and G double prime now looks like vis-a-vis our experimental data. And if you look very closely at the plot that I've just put on the board, and you may want to pause the video to look at that, you can see that there is now solid lines joining all those data points together for the elastic modulus and for the viscous modulus. The fact that it's quite hard to see shows actually that we've got a very, very good fit indeed with 8 relaxation modes. And so this gives us confidence that we can now numerically describe those experimental data that we've got, which becomes very, very useful in later stages of this experimental protocol. But for now, we can say that 8 relaxation modes gives us a good fit of the experimental data, and we'll put those data to one side for later use. So, we've looked at the linear viscoelastic region. We determined where that was using a strain sweep. We then did a frequency sweep at a linear strain to get us GI and lambda I. Now we want to look at the non-linear part of the region. And we know that the nonlinearity of the polymer rheology gives us a phenomena like shear thinning in steady shear. We've seen we can capture this mathematically using one of two general approaches. We can have, for example, a damping function built into an integral constitutive equation. A strain-based damping function, for example, a Wagner damping function, should allow us to work out what that shear thinning in steady shear looks like. We've also seen that we can use an inherently non-linear constitutive equation. We saw the Giesecke's equation was an example of that, and there are many more examples of more complex non-linear viscoelastic constitutive equations. We're going to take the first approach. We're going to use the damping function approach in this analysis. So what we're going to do is to do some step strain experiments. If one thinks back to the lesson on the Wagner damping function, what you do to calculate this function is to look at the linear step strain response, and then the non-linear step strain response, and then to do a comparison between the two that will effectively yield the damping function. So I've put two things on the board now, a plot and an equation. Let's go through the plot first. The plot is plotting relaxation modulus as a function of time after a step strain deformation. We're doing this in one of two regions. The linear region, light blue, that's 10% strain, and the non-linear region. So the remaining data points there, the pluses, the dashes, the crosses in varying colours, are for 100, 200 and 300% strain, which we know is well over that 40% or 50% strain that we determined to be the boundary between the linear and the non-linear region for this polymer. Now, if one thinks back to the lesson on the Wagner damping function, what we had was the expression on the base of the screen here. E to the minus k gamma 1, where k is the damping function, is the ratio of the non-linear modulus response over the linear modulus response. So g naught of t there is the 10% strain response. G of t is 100, 200, 300% strain. Gamma 1 in the exponential on the left-hand side is the strain, and it is imperative to note that this is in absolute units and not percentage units. So 100% strain, gamma 1 equals 1. 200% strain, gamma 1 equals 2, and so on and so forth. So we have a time series for G naught of t, that 10% strain response. We have a time series as well for all the nonlinear responses at 100, 200 and 300% strain. So what we can do is calculate probably upwards of 50 or 60 values here for k at different times, and then that value of 0.123 is an average of the whole lot. So how well does this work? Let's remind ourselves of how we calculate G of t now, using the linear viscoelastic parameters, Gi and lambda I, and our non-linear parameter, the Wagner damping function k. And on this plot, you can see there's a region where I've plotted 4 solid lines that correspond very nicely to the experimental data. And we can see that the Wagner model captures G of t very well over the region of about 0.1 to 22 seconds, which is a couple of orders of magnitude of time. So that's not too bad. Right, that's the viscoelastic characterization done. We will be using these data again in further parts of this lesson to provide some checks. Let's see now what we can do to determine the steady shear response. So the first set of experiments I'm going to do is using rotational rheometry. Parallel plates again, steady shear now rather than oscillatory. And this is where we have to be a little bit careful, because if you examine the response that I've just put on the blackboard here, it looks a bit strange. At low shear rate, there's an increase in stress with respect to shear rate, which is kind of what we might expect. Then we go through a few turning points and points of inflection, and everything seems to go a little bit haywire. What's going on? Well, what we have here is a polymer being deformed, contained between two parallel plates. If one imagines the normal forces that are set up, the normal forces are persuading this polymer to exit our experimental system. And so what we actually see here are the effects of varying degrees of decreasing containment for our polymer. At low steady shear rates, you've got good contact between the plates and good experimental data. At increasing shear rates, the polymer is squeezing out of the plates, it's starting to leave the system, and the measurements that you're getting are becoming less and less reliable. We can see this if we plot the viscosity response that we can work out using our viscoelastic data, both linear and non-linear. And if one recalls a previous lesson, we can work out the stress due to GI, lambda I and K. And if we know the strain rate, we can work out the apparent viscosity. So that purple line is a plot of apparent viscosity as a function of shear rate from the data that we've obtained from our viscoelastic analyses. And we can see at low shear rates it fits very well, but it highlights very quickly where we have a departure between the experimental data and the theory. And that departure is due to a lack of sample containment. There shouldn't be any turning points or any points of inflection even on that experimental curve. There are, and we can see it is at the first of those that the theory and the experimental data diverge. So what we have here, unfortunately, is a very large range of invalid data due to loss of containment. And this is fairly typical when it comes to the experimental characterization of polymer rheology. You'll find that one rheometer typically won't give you all the information you need for polymer melts because of things like this. So we've got some low shear rate viscosity data. We've appraised the data quality using the Wagner model. What we need now is more data, and we need to change our technique. So in order to obtain more steady shear viscosity data, we're going to turn to capillary rheometry, a self-contained system where the polymer can't escape and where we're measuring pressure drop now. So capillary rheometry has to be done with care. We've got viscous heating effects we need to be careful of. We've got all those corrections that we've discussed in previous parts of this course to worry about. So I'm going to cut a long story short here and just plot the final data. This graph is apparent viscosity as a function of shear rate. The green crosses are those data obtained from rotational rheometry. The orange crosses are those obtained from capillary rheometry after we've done the Rabinovich analysis, after we've done the Bagley corrections, after we've made sure that we haven't got excessive viscous heating taking place. And what we can see if we sort of squint and look at this graph is that, yeah, these data seem to be consistent. What we have is a low shear rate Newtonian plateau in the green, going into a shear thinning zone that looks sort of power law-ish once you get into significantly higher shear rates. Now, we can use our viscoelastic data again to help us appraise the quality of these steady shear data. And that purple line I've just put on the board is now the Wagner's model for apparent viscosity as a function of shear rate. We saw the equation on the previous slide. And so what we can see here is that it's beautifully consistent. So where the Wagner model was warning us that our rotational rheometry data was deviating was indeed very much a warning to hear, because we can see that this model with the same parameters captures now both the low shear rate viscosity and the high shear rate viscosity. And so we can now have confidence that the data set we have is really good and is of high quality, both in terms of the steady shear data and in terms of the viscoelastic data. And these steady shear data we can simplify maybe with a generalized Newtonian model. Maybe we might fit a Corot model to something like this, because that will capture that low shear rate Newtonian plateau. Or we may find that the characteristic shear rates of the process that we're interested in doing some calculations around are well in the power law region of this model. And so we can simplify the calculations greatly by making that realization. So let's recap a few key points. What we've done in the first part of this lesson is characterize a polymer melt. We've characterized part of the viscoelastic response of the polystyrene. We haven't talked about normal force analysis. Maybe we should have done, but for the purposes these data were obtained for, it wasn't necessary. What was necessary was a good knowledge of the linear and non-linear viscoelastic properties, which is what we've got. We've independently measured the steady shear viscosity using 2 different rheometers, and then we've used the linear and non-linear rheology, viscoelastic rheology, to check those steady shear data. And we saw those checks are valuable because it helped us to highlight the valid data from the rotational rheometry, and also gave us confidence in the combination of using capillary and rotational steady shear data together. And using those data, we could then get a generalized Newtonian model if that's what we wanted to do for further calculations.